limit as x approaches 0 from the right. Can anyone differentiate natural log for us? Easy.
1 over x.
Yes, absolutely, 1 over x. Now careful how we differentiate this, because it's x to negative 2, this one. And when I differentiate x to negative 2, I have negative 2 times x to negative 3, or negative 2 over x to the third. So when I differentiate this, I get negative 2 over x to the third, which is perfect. Because now I keep 1 over x, and I flip this, and I put a negative in front. Beautiful. I simplify one of the x's. I'm left with negative limit of x squared over 2 as x approaches 0 from the right. So therefore the answer is anyone? It's
0?
Yes, that's it. And you can say, and non-believers would say, see, I told you, 0 times infinity is 0. Not always. So please don't draw conclusions that 0 times infinity is 0. No. 0 times infinity is an indeterminate case, which means basically by indeterminate we mean no clue. Anything can happen. That's what we really mean. Anything can happen. But the product is not difficult. A simple algebraic manipulation will bring us back here. Now these are more cumbersome. These are the longest ones, but you will see not difficult either. But by comparison, they require way more work. And that's it with 4.4. After we work on powers, of course. We have a lot of work for powers. Okay, allow me to... We can choose differences, and we can, of course, if you want, we can do that first. See if you want to work on any of these problems. Most of these cases change into ratios because I still have to simplify. I have to find the least common denominator and so on and so forth on 51, 53, 54, 55. See if you want to choose. If not, we'll move on. I'm looking for powers now.
Can we try 55?
55 it is. So let's continue with 55. And 55 we have limit as x approaches 0 from the right of 1 over x minus 1 over tangent x. Let me make sure I copied it correctly. Yes, 1 over x, good. See, this is one situation in which I cannot say plug it in. It doesn't mean anything. So this is one exception to the rule. Plug in after simplification. So I'm not changing the rules on you, but we can't plug in 0 here because this is infinity and this is infinity. So we have to simplify first. What do I mean by simplification? Well, I have to find the least common denominator. What is the least common denominator here?
X tan x?
Yes, of course, it must be the product of the two. So then, of course, this one needs an adjustment of tangent x and this one of x. So this is tangent x minus x. Now I have to plug in. And we know that this is 0 and this is 0, so the numerator is 0. This is 0, this is 0, the denominator is 0. Beautiful. That's all I wanted. Every time I see 0 over 0, infinity over infinity, it's a piece of cake, so to speak. But L'Hopital's rule. I have a limit, I have a function, I have 0 over 0. Limit as x approaches 0 from the right. Now I have to be careful because when I differentiate this, it's a product. This one is not, but this one is a product. So can anyone help with the numerator, to differentiate the numerator? Anyone with the numerator? Anyone would like to help differentiating the numerator, please?
That'd be secant squared x minus 1.
That's it. Thank you. And now we have to use the product rule. Can anyone help with x tangent x? Anyone, please? X tangent x.
It would be 1 times tangent x, so just tangent x.
Yes, plus x.
X times secant squared x.
Very good. Awesome. Now we have to look at the numerator. Well, when we plug in 0 in secant, it's still 1, and 1 minus 1 is 0. When I plug in 0 here, 0, and 0 times non-zero is still 0. Okay, beautiful. Next step, we do it again. So this is limit as x approaches 0 from the right. Okay, now I have to be careful how I differentiate secant squared. 2 in front, secant to 2 minus 1 times the inner function prime, which is secant x tangent x. So let me go through this again. Secant square prime is 2 times secant to 2 minus 1 times the inner function prime, which is secant tangent. Negative 1 prime is 0. Now, secant squared, but here I have to differentiate using the product rule. First function prime is 1 plus secant squared x plus x times, and I have the same derivative, 2 secant times tangent, because I have to differentiate secant squared again, which I already did at the top. So 2 secant x tangent x. And now let's see. This is 1. This is 1. All this is 0. This is 1, but this is 0. So then the numerator goes to 0, and the denominator goes to 2. Fine. 0 over 2 is a number. What is it?
0.
That's it. That's it. So don't be afraid of something like this. Just remember, don't plug it in before the simplification, because you're not going to be able to conclude anything. So you don't really want to say, okay, this goes to infinity and this goes to 1 over 0 from the right. So, right? So, but after you combine like terms or subtract these fractions and find the least common denominator, then this is so much easier to handle. Good. Okay, so let's see. Now we got to do powers. So 57 on deals with powers. So allow me to choose the first one, and then you choose the next one, because this is a longer procedure. I'm going to choose, oh, you tell me what you want, 57 or 59. Which one would you like us to work on?
57.
57. Okay, let's start with 57. I'm on page 7. Good. 57. So we have limit as x approaches 0 from the right, from x to power the square root of x. Perfect. Okay. So remember, we have 1 to infinity, 0 raised to 0, and infinity raised to 0. The most cumbersome ones, they are the powers. Okay, so let's start with, doesn't matter. Let's start with the base. When x approaches 0 from the right, the base approaches
0.
Excellent. When x approaches 0 from the right, the square root of x approaches
0.
of course. So we are looking at the situation 0 raised to power 0. Remember, we always say a number raised to 0 is 1 as long as a does not equal 0. This is what we learn in algebra. Because we cannot in algebra explain what 0 over 0 raised to 0 is. So that's why we put that condition. Any number raised to 0 is 1 except when the base is 0. Okay? When the base is 0, and like in this situation, 0 raised to 0, this is an indeterminate case, one of the 3 powers. Okay, awesome. Good. So then, anyone remembers what we did when we had a function, f of x, raised to another function? I know this is not what we are trying to do now, but can anyone refresh our memory how we apply what we did in this case? A long time ago. How did we differentiate a function raised to a function? What was the rule?
Isn't it like the function prime, or like the inner function times the prime of the inner function, something like that? Or g of x times the inner function prime. I don't know. I forgot.
So remember, we specified it's a trap, right? So it's very easy to fall into that trap. If this is a number, then we bring down the number, we subtract 1 from the power, and we differentiate the inner function. Done. But if this is a function, we have no rule. We have a several-step procedure after we apply log. So I want you to see the correspondence here, or maybe the similarities. I have the same situation. I have a function raised to a function. It's an identical situation with a function raised to a function prime. Yes, I know we're not differentiating. We're finding the limit. But this is what I have to do. I have to name the function. I have to apply natural log to that function. So in step number 1, it's a long procedure, has many steps. There is no rule for this, so we name the function. Step number 2, we apply log to both sides. Step number 3 now, because we are not differentiating, I just want you to see the similarities. We are applying the limit. So I'm applying the limit to both sides. So apply not APRLY, it's APPLY. Sorry about that. I'm not sure what I did here. Okay, better. So apply limit to both sides. Okay, so let's do that. So I apply the limit as x approaches 0 from the right from natural log y, and to the other side limit as x approaches 0 from the right from the square root of x times natural log x. I know you're going to say, wait, stop. What are you doing? You're asked to find the limit from x to the square root of x. Why would you apply the limit to natural log? I'll explain in a moment. So again, there's so much more to it, but let's go back and summarize. Number one, I take the function and name it y. Step two, every time I have one of these. Step one, because they are similar to this. So step one, I name the function y. Step two, I apply natural log to both sides. Step three, I apply limit to both sides of this. Leave this alone. Don't even look at it. Let's find this limit. When I find this limit, I realize that this approaches 0 and this approaches infinity. Nice! Product. 0 times infinity. So what did I accomplish? You can say not much. Well, I'm on the way. I changed these difficult situations for now into this one. What did we say? How do we deal with a product? What was the technique for the limit of a product like this? What did we say we needed to do for the product?
Apply algebraic manipulation.
Awesome. Awesome. Play with the function to change it into this or 0 over 0. So how will you play with the function? Not with natural log. Never touch natural log. So I have the limit as x approaches 0 from the right from natural log x over 1 over the square root of x. Exactly how we did it with x squared. So I changed it in the previous problem x squared into 1 over x squared in the denominator. Don't say the square root of x here and put the square root of x here. No, it's 1 over the square root of x. Because when you flip this, you get that. We're not allowed to change the function. We can change the presentation, but not the core, right? So, and then I'll proceed. Yes, these are cumbersome. These are not easy situations. So then I have limit as x approaches 0 from the right from natural log over, and the denominator is x to negative 1/2. 1 over the square root of x, x to 1/2, change into x to negative 1/2. And now, as x approaches 0 from the right, I know this is negative infinity. And here, as x approaches 0 from the right, 1 over 0 positive will be infinity. Not a nice problem, but we need to see those. It's a very good pick. But now finally, I love this. So I know there are many steps still, but let's summarize what we did. So after we labeled the function, we apply natural log, and now we apply the limit, and we struggle a little bit with this because it's not a nice limit. So first, initially, it was a product, but now finally we were able to change it into a ratio after all this hoops and loops. Because of this, I can differentiate using L'Hopital's rule. So I have limit as x approaches 0 from the right. Can anyone give us the easy function? And then I'll do the difficult function. The easy
1 over